officially recording. Forgot to record my first class today, so
Oh,
yay
that's
me.
awesome.
Yeah, I remembered to screen share and then I forgot to record. But no, I'm going to get the screen share and the recording going for y'all. I can learn from my mistakes. So first thing, you need to get some more of your classmates to do evals if you want to get all the extra credit. You're at 20 out of 29 was the target because there's 32 of you. So have until Saturday night to work on those. I plan to send a reminder tomorrow to folks who have not completed them, since that is an option within this thing. The Qualtrics survey is open until next Thursday, though, so you can work on that after you finish your other stuff. So no homework questions right now. If any come up, as a reminder, I have office hours every day next week, Monday, Tuesday, Wednesday, and Thursday, as noted on the syllabus. The TAs do as well. So come on, come all, get your stuff finished. And I know this is a difficult point in life, like the crunch at the end of the semester, but it is finite. Like, for better or worse, on December 21st, like, it's done. So if we can just hang in there for a few more days, then you can have some time off. Or go back to the rest of your part-time and full-time jobs, right?
Yes.
Off from the worrying of classes, I'll put it that way. All right, then if there's no questions, things you want to chat about, we dive into stuff? No?
Dive away.
Okay, we're diving then. Yeah, so lecture 6 happening today. The finale. Caveats and next steps. So I wanted to review what we've talked about and make sure that you have the vocabulary to describe the kinds of models you are now able to do, and then to talk about why you can't just take this class and think that you have enough quantitative methods to do everything you would want to do in your research and your life. So this is kind of a sales pitch to keep going, but it's also important to recognize when the tools you have are not adequately situated for the job at hand. So that's the big picture here. Question? No? Okay, there. No worries. So this was the first slide at the beginning of the semester. It said 2 reasons why you are here, and now it's 2 reasons why you were here. This class fulfills a requirement, and I just need to pass it. That is a perfectly valid reason for being here, but I hope to have convinced you on the utility of learning quantitative methods. So I know this class is called Statistical Methods in the title, but I don't like that terminology. This is a class about quantitative methods and how to use models to answer research questions. And the scary part is not the math. The scary part is the working memory load that it takes to manage all of these things together. And that will continue to be the case if you were to take more advanced coursework. So an important component of doing quantitative methods research responsibly is recognizing when you have the right tools and when you may need to get some additional tools in your toolkit or some additional consultation or help with your process. But first, let us review. So a sequence of steps in an analysis using general linear models. Number 1, what's the question? Understanding the research questions to be answered, and then what are the relevant variables and needed to answer them. That's always the first thing. This will dictate which variables involved and how they are specified. So the 2 choices that we have really for this in terms of the role of a variable in a model is predictor versus outcome. And these are my generic words. Here are some synonyms for you. The word covariate sometimes has a special meaning as a predictor that someone else cares about who's not you, but that just means predictor as well. Or dependent variable is a synonym for outcome. The main thing I want you to take with you is kinds of variables as being quantitative or categorical. There's other specifications within that. Quantitative variables are numbers or numbers. Categorical variables, numbers or labels. So we can have binary, where there's just 2 choices. That we can have nominal, where they're unordered categories, or ordinal, where they're ordered. But the key idea here is that they're not numbers. And so we have to do things differently because of that, even if the data are stored as numbered. And a bummer, potentially for you, is that all of the models that we've been working with this semester are only for quantitative outcomes. It's not a coincidence. I know, right? But do you think that you could predict a binary outcome? Like whether or not a student graduates? Is that a reasonable thing one could do?
Yes.
Yeah. So the good news is that you have all the skills that you've learned, you will add to be able to predict binary outcomes or ordinal or nominal or things like that. Like, it's not going to be undone, but there's just extra concerns in that case. So as an example, what is the highest value that a binary variable can be? 1. What is the lowest value it can be? 0. If I fit a model where I have a slope going through a predictor, that slope could predict from 0 all the way up to 1. It could predict 1.5. It could predict 2, right? It could predict something negative. The slope needs to understand that that has to shut off between 0 and 1. So there's ways to do that to make sure that the model doesn't generate predictions that are out of bounds, for instance. So there's extra layers for things that are categorical as outcomes, but using a lot of the same concepts and processes. So determining how to include predictor variables then is something else that we would want to think about. So if I have a quantitative variable, it should be centered. So that means rescaling it by adding or subtracting a constant so that 0 is a meaningful reference. Now this isn't strictly necessary in the sense of screwing something up. Like if you skip this step, your R-square will be the same, the predictions will be the same, but the consequence is that some of your parameters may not be interpretable. So for instance, the fixed intercept for sure, because that's always where your predicted outcome is conditional on your predictors being 0. So that would be 1. And as we saw in the last unit, the main effect slopes are conditional on any variable they interact with being 0. So we want to have meaningful zeros for those reasons as well. So there are no wrong choices for centering constants, only weird. This is a choice you get to make as a researcher. So I specify what the constants are in my homework instructions so that we can all arrive at the same solution, but it's up to you in life how you do that. Then we got to think about how a quantitative predictor might be related to the outcome. And this should be driven partially by theory, but also partially by the patterns in your data. So linear is the default, right? We add in a slope, that is the change in y for a 1-unit change in x. But the effect keeping going no matter where you are may not be plausible for a lot of contexts. So we could do things like add the squared predictor, creating a quadratic trajectory or a parabola, a U-shape, happy face or sad face. If you log transform your predictor first and then fit a linear slope, the result is something that looks more like exponential. So it comes down and kind of levels off, or it goes up and levels off like that. So that's good for the idea of diminishing returns. More money doesn't always help, for instance, if we have something like that. Piecewise models or splines, if you have a predictor that is characterized by distinct regions, like maybe a subclinical area of depression versus a clinical area of depression. If you have hypotheses that something would matter more depending on where you are on your predictor, those can be implemented with linear spline models. And you can always look at the means in your data to help you decide these things. Predictors that are categorical, we cannot put them in straight as they are. Even if they're stored in your data as 1, 2, 3, if 1, 2, 3 are 3 different groups, it won't make any sense. So this is where we have what is called dummy coding, which is a term I really don't like anymore. I'll say binary coding. And we need C-1 new predictors when we have C categories. Do you remember why it's -1?
Because your reference is the 0.
Because one of the groups is the reference.
Or the control group.
Yep, so the intercept is the 1. So if I have 2 groups, then I have an intercept and 1 slope that gives me the difference between the 2. That's 2 fixed effects. If I have 3 groups, like here, I would need to add, or this is 4 groups actually, 3 groups, I would need to add 2 new predictors, 3 predictors for 4 groups like this. So the 2 coding schemes that I demonstrated this semester are 2 of many, many possibilities, by the way. There's like whole books about this, but I think these are the 2 that are most useful and common. The default in a lot of packages is this one that your textbook calls indicator coding, and I think this is most useful for nominal predictors. So in this coding scheme, you would designate one group as the reference, such as group A here, and then you stick 1, 1 in each of these that designates the difference for the other group. So then I named these because this would be how A differs from B, and A and C, and A and D. But the direction of the slope would be, like in this one, it's how the D group differs from A as the reference in this case. And I have a star here. So you know how I made you like make all the groups, like when we did the golf homework, you had to make the things? Yeah. What if I told you that there's a faster, easier way? Ugh. I know. So there's in R, there is an option for factor is a kind of variable, and then R makes the demicodes for you and puts them in your model. In Stata, the analog is instead of C dot, instead of a predictor, it's I dot, and it does the same thing. Now you might be saying, hey, are you just mean? Like, did you hide this from us on purpose? And the answer is yes, I did hide it from you on purpose. Because when you have a factor variable, all the logic of how you think about these group differences and build conditional means is hidden from you. Like, you don't see that happen. And so the method of creating them yourself and then adding them to like an equation corresponds much more directly to the linear model's representation as to what is actually going on. But once you understand the underlying logic of how this works, I think it's perfectly fine to take shortcuts and use these features to save yourself some typing. This is especially helpful if you have like 10 groups, right? Because then there's commands that you can say in one line, spit out all 10 means, or spit out all possible differences between the 10, and like that 2 lines of code as opposed to 8,000 layers of zeros and ones statements. But but the code is executing essentially the zeros and ones for you. So this is the only way, though, that I know of in R, at least. There may be choices in Stata related to kinds of IDOTs. This is what it does for you, is this one. The alternative, sequential coding, is something you probably would have to do manually. And this one, I think, is more useful for ordinal predictors, because what it gives you is like the adjacent category differences. So A is still the reference group, but the first slope gets you to group B. The second slope would then get you from B to C, and the third slope gets you from C to D. So then you can think about, like, as you move up one category, what is the impact on your outcome? And this coding scheme also kind of illustrates why you would not want to put a categorical variable in as if it were numbers. Because that's the same thing as saying that each of these slopes that would be in the model is equal. The change between A and B is the same as the change between B and C is the same as the change between C and D. That's a linear slope. So by putting in 3 different slopes, we would actually get a chance to test whether you can pretend that they're numbers or not. Another strategy of choices for coding is called effects coding, and that is usually a bunch of plus or minuses ones, so that things average out, so that like the intercept is the grand mean across all of your categories rather than for a reference category. I don't like that, because then your intercept isn't meaningful, because there's nobody who's at the mean of all the groups. They're either in one group or not. So I don't prefer that as a strategy. So these are the 2 that I would recommend going with you. Then the question is, what else do I need to answer my research questions or fully describe my results that's not given to you by default? So this is the idea of using lincom in Stata, or GLHT in R were the options I taught you to generate things like predicted outcomes for non-reference groups, differences between non-reference groups. So in the previous slide, for instance, I am only going to get 3 of the possible 6 comparisons that I might care about through either of these methods. I can use those post hoc estimation commands to get the remaining 3. So here's some examples of things that we did. Differences between non-reference categories, differences between fixed slopes. So is the difference between A and B equal to the difference between B and C? That's a comparison you can ask for. It also would make sense for any predictor slopes being on the same scale. So for instance, one of the homeworks that I have, I think it's in the generalized class, is predicting the probability that you will get a job after graduate school from the number of papers and the number of conference presentations. So those are on the same scale in the sense that it's one more product that you would add to your CV. And one of the questions that I ask is, are these slopes equal? Like, all things being considered, should you put more effort into another paper or another presentation?
Interesting.
Or if you think about risk factors, for instance, if you have this characteristic, that's a risk factor, or you have that characteristic, it's a risk factor. Are the risks equal? That's a question you can ask by comparing slopes. We also did this for what are known as conditional or simple slopes for predictors at other values of the moderator. So in your homework, for instance, what is the effect of verbal ability if you're playing an easy opponent? What is the effect of verbal ability if you're playing a hard opponent? The latter is going to be a linear combination that's not directly given by the model. So there may be things that you want to know that are part of the model but not part of your output. And so hopefully you've learned some techniques on how to get those. You may also need to lump slopes together. So some questions are answered by a joint set of slopes, such as for a categorical predictor. So do the 3 slopes work together to differentiate the 4 groups? That's one question. Or if I add these new predictors to my model, do they change the R-square significantly? And you can ask for F-test to do those as well. So that would be test in Stata, and it would be GLHT in R, or various other ways that I've shown you. Hierarchical LM is one that comes to mind as well. So, okay, with me so far? This all should sound like review, right? Good deal. That's my goal. So reviewing the steps then, number 5, effect sizes. So we want to report hypothesis tests and p-values because the world still uses them. There are valid reasons to not put as much importance into them. I try to give the readers anything they might possibly want to know. So I report p-values and I report effect sizes, and I can let them figure out what they want to pay attention to. So what is always okay to report would be partial R's or Cohen's D's per slope. So we can talk about those. So effect size is the idea of standardizing how meaningful the contribution to a model is for a predictor. So these are useful for anticipating power for future analyses, like somebody who's planning a study on a similar topic may appreciate this information to help them plan their study. It's not as useful in relation to the model R-square, because these are the ones that talk about how much variance the predictor explained beyond what was already explained, and that's the part that makes it somewhat confusing. This is also the version of effect size that can be artificially inflated by adding terms to your model, like favorite color, I think was Sam's example, in predicting whether a student's going to graduate. That might explain some variance, but it's probably not going to help you build a better program. The ones that can be okay are per slope semi-partial squared. So that is the amount of the R-square in total that is due to that predictor. But these you need to tread a little bit carefully with. If you have binary coded predictors that work together to represent category differences, you need to lump those together because they're not independent. The same thing with respect to main effects and interaction terms. If you have an effect size for a main effect, recognize that it's only conditional on the moderators being 0. So you could have a different effect size if you chose a different centering strategy, which makes it a little bit, a little squishy, I would say. And the most important thing, write it up and turn it in. So you will hear me say this throughout coursework and advising. At some point, you got to stop running models and decide what your story is going to be. Now, ideally, it would be like, I have my data, I have my question, I run a model, and it answers it, and I'm done. But in life, that's not likely to happen. There's always some kind of iterative process where you try to figure out what is needed and what is not needed, and not overcomplicate things with respect to your readership. So my advice would be only to report the models that tell the honest story in answering your research questions. So not pretending like you knew what the right answer was all along, but not potentially telling them about all the rabbit holes you may have gone down in trying to figure that out. So the things that you would report: analytic method. So there should be a paragraph at the end of your method section or at the beginning of your results section, depends on the journal, that describes the general approach. So you would say something like, we estimated general linear models using Stata version 18, or using R this version and the particular packages and their versions. You would also describe how the variables were set up, so what your coding strategy was, who the reference group is, what the centering was, all that kind of stuff. Equations can be useful to help convey this if you use the proper notation. So I would encourage you to use either LaTeX or the equation editors within your Word documents or Google Docs or those things so that the equations render properly. And then what happened? So the what happened part is you're having a conversation with your reader while you are simultaneously giving them all the information that they would need to interpret things by themselves. You also want to go through the extra step of making sure that they understand what your conclusions actually mean. So I have a very formulaic way of doing this that's in the examples and in your homework. Like, there was an effect, F comma this, comma P comma this, comma, and then the next word needs to be something like such that, or indicating, or something that is like putting that into English, such that the groups were significantly different. or this group was significantly higher than that group, or there is a relationship between these as X goes up, Y goes up, something like that that goes with it. Because that's the part for your readers that they're going to highlight in your paragraph when they go through your article. They're not going to highlight the F, I guarantee it. It's not going to happen. So per slope, you would want to report either in the text or in a table, but not both usually, estimate, standard error, p-value, and effect size. I don't think it's useful to report the t because they can get that from this, and the p is really the thing that people care about. I like reporting exact p-values over stars, but if you are short on space, then you can do like a star for things that are significant. I don't prefer when people have like 1 star for p less than 0.05 and 2 stars for p less than 0.01 and 3 stars for p less than 0.001. It's like, no, get off the fence. Like, you set your alpha, like, stick to that, right? It gets cluttery. I don't like it. In R, by the way, there's an option that I shut off in my R programs at the very top that shows the stars or not. You can turn that on, and then your output will have the stars in them if you prefer seeing things that way. It's a choice. So slopes, this is what you would want to report. Per model, you would want to have an F, both of the degrees of freedom, the residual variance, and then the R square and p-value for the model, and making them tell them why they should care. So with respect to research question 1, we found this, F blah, 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 indicating that. Like, tie the whole thing together. And I would also encourage you to think about using supplemental material. So nowadays, journals are all online, paper barely exists, and that means concerns about page limits have somewhat gone away. So if your journal still has, like, you need to have a manuscript that's 30 pages or less, and you have other results that you'd like to share but aren't really as important or critical to your story, you can create an online appendix in which you report additional things. You can also give them your code. Like, you can write a syntax that you used and be completely transparent as to how you got everything. And these kinds of additions that give additional explanation or resources can help get your paper cited for that reason. Like, following Hoffman 23, we did it this way. That kind of thing. So what did you learn this semester? These are all the words that you can now say that you know how to do. So we did general linear models as a one-stop shop for predicting one quantitative outcome from a person. And if your predictors are quantitative, we would call that linear regression. Sometimes people drop the linear. One numeric predictor would be simple linear regression. More than one would be multiple linear regression. And this includes, in this class, other forms besides linear. If you have categorical predictors, most people would call that analysis of variance or ANOVA. If you have one two-group predictor, some folks would call that an independent sample t-test or an independent groups t-test. If you have 3 or more groups and you have one predictor, that is a one-way ANOVA. If you have 2 or more grouping variables, then that's a two-way, or a factorial is another word that people use to describe that because it typically includes interaction terms. And if you have both kinds, some folks would call that analysis of covariance as well. So I don't teach it this way because I think it makes it more complicated than it needs to be, because these are all using the same ideas and the same processes. But these are the words that you could also give your reader to describe your model that might make them more familiar with what you're doing. So the missing step 2, I went from 1 to 3 on purpose. What did I skip? Making sure we have the right model in the first place. And I made a choice in this class to put this off until the end, because I don't think it's helpful to say, this is what has to be true or your model doesn't work, without telling you what you can do instead if it's not true. So this is both a sales pitch to get you to come to future classes, but also cautionary tales for things to watch out for. So several things need to be plausible for the modeling results that we've been looking at to be believable. These are what are known as model assumptions. Like, we assume these things are true. There are 2 different kinds of consequences. They can show up with respect to the fixed effect estimates, and they can show up with respect to the fixed effect standard errors. And these are 2 distinct kinds of problems. So if I have the wrong estimates, then I have the wrong story in how these things relate to each other. If I have the wrong standard errors, then I have the wrong p-value for my story. So two distinct problems. Some of these things can be fixed by modifying the code or the process that's being implemented, and some of them can't. So let's start with what is actually assumed, and then we can talk about what you do instead. The first one, I can't even tell you how many times I've read this, that linear regression assumes linear relationships. It is not true. As a general rule, your model assumes that it's right. So that means if all you put in are linear slopes, you are assuming there's a linear relationship. But if you put in something else, you're not. So we can have non-linear relationships in a multiple linear regression model. That's totally fine, and we've done it all semester. So non-linear in the variables is what I'm talking about. That means adding predictors that create a non-linear relationship, but you're adding them within a linear model. So like if I have a slope of x and then I have another slope of x squared, that's a linear model because it goes constant times variable plus constant times variable plus constant times variable in this additive fashion. But you're creating a non-linear relationship by including x and x squared. The alternative is something called nonlinear in the parameters, and here's an example of one of those. It means it breaks that functional form of constant times variable. So like this kind of model is an exponential model. Beta 0 would be something called an asymptote for optimal performance. Beta 1 is the amount of change that happens across x, and then E is E, whatever that number is, 2.71 something. Euler's constant?
71828.
Yeah,
Like that.
it's
Yeah.
a number. So this would be like E to this slope times x. That breaks the form. So this is a truly non-linear model in that case. And there's many flavors of those. These are harder to estimate and less common. So I would say as a take-home point, your model assumes that your predictor effects have been specified correctly. If you put in quadratic effects, it means you're assuming you have a quadratic relationship. If you don't, it assumes linearity. And that is true in every model, not just general linear models. Otherwise, your characterization is going to be incorrect. So things to watch out for would not just be nonlinear trends, but also interaction terms. If your predictor is specified to have the same slope for everybody, but it actually isn't true, then that slope is not going to be an accurate representation. So this, I would recommend adding things to the model to see if they're needed. That's an empirical way to decide whether your model is good enough. You're also assuming that any variable that's not in the model would not contribute to it. But you can't do anything about that. It may not be in your data set. So if you haven't measured it, there's no coming back from that. Is normality an assumption? Now this is a big one and it's often confused. So of the predictors, absolutely not. Predictor variables have no distributional assumptions about them whatsoever. You can add any kind of predictor you want. Here's the tricky part. Of the original outcome, no. So one of the things that in regression, you'll see this, that we assume normality and constant variance and independence. Those are going to be the three. But normality of what is the question? It is not the original outcome. It is what the outcome is left over, conditional on your model. So in the models we've talked about this semester, they are for plausibly continuous or continue-ish outcomes whose residuals should have this kind of shape. The e's should be normal. That means your original variable could have a lot of different shapes to it and have it still be fine. So if you think about having a strong grouping effect, let's say that you have an outcome where you have a control group versus a treatment group and they're very, very far apart. What would Y look like as a shape before you put anything into the model? Like if you just plotted it. If you've got two groups in there and they have a very big difference. It'd be like two humps, right? Like bimodal. Well, bimodal is definitely not normal. But once you control for which group someone's in, hopefully they squish together and they would look something like that. Now, why I'm harping on this is because many textbooks have standalone chapters on data cleaning, outlier removal, and transformation. Like Tabachnik and Fidel is a very well-selling multivariate textbook, even though most of it's not about multivariate models. And they have a whole chapter on square root transformations and log transformations and Windsorizing and checking people out and stuff like that. But here's the thing. We don't have residuals unless we have a model. So it makes zero sense to worry about transforming your data to make it normal if you're just looking at variables and you're not looking at residuals. So residuals are supposed to be normal. That's the idea here. Now that is not always going to happen. The other one that goes with it is constant variance. And there is a fancier term for this. Homogeneity of variance, homoscedasticity. Do you know what it means when you have not constant variance? Have you heard that word before? Heteroscedasticity. I'm not making this up. That's actually what it's called. There's like 17 syllables in that word. Not constant. But here's the thing. Here's why we think that way. Because we are using the normal distribution as the way that we can figure out what the most likely estimates are for our data. And the normal distribution only has one variance. So we're assuming that one variance holds for everybody, regardless of your predictor values, regardless of your predictions. So it turns out, and you'll see this next semester, this is why I have likelihood here, that minimizing the sum of the squared residuals is equivalent to maximizing the likelihood, which is kind of like the probability of something happening, but you can't use that word because it's a continuous distribution. So more on that later, but the normal distribution is our definition of height in figuring out what the model should be. And that definition only has one spot for variance in it. So I stole this picture from these places here because I really liked it and I didn't want to make my own. Fair?
Fair.
Yeah, fair, yeah. So thank you, whoever made this. This is a plot of X as one predictor here on this axis, Y as another one, and then we're showing the regression line of how X relates to Y, and the little humps over it are depicting the idea that the scatter of the points around these lines should have the same spread no matter where you are on the line. So E is 0 if you're right where you're supposed to be, like your Y is predicted accurately for your X, but then that's not going to work for most people. You're going to be wrong to some extent. And so the extent to which you're wrong should not differ based on where you are on X or Y. Like the model should work equally well for different kinds of people. That's the idea. Now that's not going to happen for many different kinds of outcomes. So I stole this picture because I really like the labels. So here's an example of residuals that are spread out evenly along the regression line, and here's an example of when they're not. So not good. So this is heteroscedasticity, or non-constant variance. Now this happens really commonly in outcomes that are bounded at 0. Because like if you have a count of the number of times something happened, there's only so many ways to be wrong if you're predicting a count of 0 or 1. You can get a lot wronger as you go up. So in practice, the normality part is not as big a deal as the constant variance part. Because if some areas of your data have more error and some have less, aggregating over that into some kind of average means you're going to be conservative in some spots and too liberal in others. So we can fix that. Here's examples of when you might see this happen. Proportion correct outcomes. So anybody here model percentages or proportions in their outcome? Like proportion of time, time on task, something like that? Proportion correct? That's a common sort of thing to look at. Anything like that in the education land, Sam? Yeah. Any proportions? Proportion of admitted students, proportion of students getting financial aid, maybe something like that.
Well, proportion of students getting a question right on an exam.
Yeah, proportion getting one question right. Yep,
Or,
yep. So that's a common kind of outcome, but it's not continuous because the lowest a proportion can be is 1 and the highest, or 1, there we go. The highest it can be is 1, the lowest it can be is 0. Yes, I do know what numbers mean. I'm just at the point in the semester where I may forget a little bit. So in practice, what's going to happen is that as the predictions get closer to these boundary points, the error around them is going to narrow down to eventually being a constant. Like if the proportion is 1, then everybody has a 1. That's not a variable anymore. So residual variance needs to shrink as you approach the boundaries. The same thing will happen in a count outcome. So here is what's going to be example 3 in the generalized linear modeling class. This is a count. This is from a study in which people were brought into a lab and deliberately pissed off. IRB says it was totes fine. And these are people, I think, working in partners, and the outcome was after people were deliberately pissed off, how many mean things they said. Excuse me, the number of aggressive verbalizations. So one jerk decided to say 24 mean things, and the rest of them not as much. Fortunately, 45% of the sample decided to be polite and not say anything mean.
That's pretty high.
There were different conditions, so some people were not aggravated as much as other people. So there's
Fair
a whole
enough.
there's a whole story.
There's
I'm collapsing
other-
over it. Yeah.
yeah.
So how would you describe this distribution?
Exponential.
That's
Sorry.
one. How about skewness? Is it positively skewed or negatively skewed? That's from like the first week of class. We're going all the way back.
I remember, but I won't say I already
Negative.
answered one.
Negative.
Positive.
It's where the tail goes.
Yes.
Is the name. It's positive. Yep.
Okay.
Negative would be everybody's at the top and coming down that way. So this is not normal, right? We can agree that this is not a normal distribution. It's not, absolutely. But it doesn't have to be. The residuals have to be. And so if I fit a normal model, and then these are diagnostics that SAS spits out in particular, I have a histogram of residuals, still not normal. This is something called a QQ plot, which points, the line is like what was supposed to happen, and the dots are not on the line. But more problematic besides those things is this pattern right here, where as we get higher and higher, this is Y hat essentially, yeah, the spread gets bigger. So there's more room to be wrong if you're predicting higher counts than lower counts. So this is an example of where like a general linear model is just not going to work for this problem. And the student in question came to me to ask which kind of data transformation she could use to make her data look more normal. And I was like, no, like you have a pile of people. There's nothing you can do to make that not a pile of people. But what you can do is pick a different distribution. So where she ended up was a count model in which the mean and the variance are tied together. So as the mean increases, the variance increases. It's exactly what the picture shows. It's called a negative binomial distribution, actually. So we'll do that next semester as well. So then she did the exact same kind of analysis in terms of looking at the effects she cared about, just using a different distribution underneath it. It worked a lot better. So that's one example of when like that would not work. So what do we do about it? Residual non-normality is not really the problem, it's the constant variance part. So for outcomes that are sufficiently continuous, like if it's not this kind of problem, it's just something to where it's like, maybe, I'm not sure if that's a problem. There is something that you can do to change the way the standard errors are computed. So this is something called heterogeneity consistent standard errors. And there's a term for this. I'm not making this up. They're called sandwich estimators, like food. And the way that this is always explained when I read it in books is that the predictors are the bread and the weighted residuals are the meat inside. And there's like four or five different permutations of this. Now I'm going to be very honest and transparent with you. That is the level at which I understand how this works. That's it. I got nothing else. Because every source I read about this uses these words and then presents a whole bunch of matrices. And I'm like, I got nothing. So this is something that I would like to learn more about. I know that it's available in most packages, and so I just wanted to show you a couple examples of what that would look like. Other things that you can do are jackknifing or bootstrapping your standard errors, which are resampling techniques. So in a jackknifing process, what you would do is take one person out of your model, rerun the whole thing, collect the results, then take the next person out, rerun the whole thing, and do that for everybody. And this is, by the way, one line of code. This is not you manually doing any of this stuff. Same thing of Same idea as bootstrapping, because bootstrapping is sampling with replacement instead. So this is a very common thing that you will see people do. And it is useful for when you don't trust the standard errors are right because of this heterogeneity of variance problem. It's also useful if there is no easy formula to get a standard error. So like if you compute a brand new statistic that you care about and there's no formula off the shelf to get a standard error for it, you can use this technique to get one. So it's very flexible in that regard. So here's an example from example 5, predicting cognition in old people. I know for a fact that the outcome residuals are normal because I made up the data that way. Okay, I played God, I controlled everything, and I made a data set that meets the assumptions because it's made from the assumptions. So this is a model that is incorrect because it's missing the sex by dementia interaction that we added in the last class. So I deliberately left something out just to show you what might happen. So even though this picture, like if you look at this, it's like, that doesn't look too bad, right? That looks normal-ish. It looks bounded maybe, but otherwise it's fine. These would indicate a problem. So we see greater heterogeneity of variance as y hat increases in this case, because the prediction is not quite what it's supposed to be. So I fit this in SAS. Since I haven't shown much SAS this semester, I thought I'd throw one in. This is PROC-REG, which stands for regression. And this one little option right here, these things in blue, add extra columns to the output that show you heterogeneity corrected standard errors. So I have these in bold so we can just eyeball these. For most of the terms, these are pretty close. So correcting for heterogeneity didn't make a lot of difference, which is reassuring that the model wasn't too broken. But for a few things, it does. So dementia NC, for instance, that standard error changed quite a bit. The other one that changed, let me find it again, is, let's see, I think it's just that one. Yeah, this one's a little bit different too. And that makes sense because the model is missing an interaction between these things. And so those were the ones that are most affected. Here is the income data that we played with in the earlier part of the semester. It's a mess. Okay? There's no other way to say it. It is real data though, so I don't know what the generating distribution should have been. The residuals, again, it's fine. It's normal enough, fine. But then this is a mess. So heterogeneity of variance all over the place. There's a lot more variability in predicted income as you get higher because income is bounded at 0. So this is a variable that actually, ideally, would not be predicted by a general linear model. So here's Stata code. Stata, folks, it's these characters at the end here, VCEHC3. That adds an option for heterogeneity corrected standard errors. So I have the original output that we looked at in example 4 on the left here, and then the corrected versions over here. So robust at the top, and then bootstrap at the bottom is another one. So you can do bootstrapping instead by adding in these. And look at how different things turned out. So for instance, LVU had a standard error of 2.7. It went up to 4. And it became non-significant. Let's see, there's another one that was really different too. Graduating high school, that one changed quite a bit. The one for the constant changed, although we don't necessarily care about that. And then here, down here under bootstrapping, these numbers are a lot closer to these. So the take-home message is if your results change, you should be nervous. The heterogeneity corrected ones would probably be more reasonable to support, either through this process or through the bootstrapping. Here's another one. Problematic participants. Vocabulary for this to me is very confusing. But the idea is that some folks would say, well, you need to worry about outliers. Well, what kind would be the next follow-up question? Because there's 3 different kinds here. If you have somebody who is extreme on y only, that is measured by something called distance. So their x is perfectly within everyone else's. If you have someone who's extreme on x only, that is quantified by something called leverage. So this person is an outlier with respect to x, but not y. But then here's the big one. Person C up here. If you take them out, What do you think about this pattern of dots right here? Does that look like there's a correlation there? Not really. And this plot was generated to make that point. So the only reason there's a positive line going through these dots is C is pulling it up. So that's where the problem comes in. And there are ways of quantifying this, such as Cook's distance, how much the y hat would change if you took out that person. It's actually an influence measure, even though it's called Cook's distance. df beta is how much the slopes would change if you took out that person. And these are things that you can ask for in code. You don't have to like manually go through this process. But then the question is, what do you do about it? On the one hand, it seems kind of unfair for person C to have more input into what the slope would be than anyone else. So from that perspective, you could make an argument, well, maybe I get rid of them. On the other hand, is person C part of your population? Like, are their values plausible, believable, and representative? Like, if so, then it's kind of hard to argue that you should kick them out. And in reality, you're going to have cases that are like trickling away from the plot in between. And then it's like, well, where do I set the cutoff? So this gets to be very difficult to defend the more arbitrary it is. I would say that if you have concerns about outliers, a reasonable thing would be to report the results both ways. And so you can talk about how much this person has changed the picture, and your readers can decide which version they believe. So for instance, in my dissertation, I had 155 older adults. There were 3 folks who were really extreme on one measure to the point where the measure was unrelated to my outcome if they were not in the sample. It was related if they were. So I had to talk about that. Like,
Both results?
Yep. So the answer changed based on whether these people were included. That should make us a little bit nervous. Okay, questions or comments? Cheers. Back to water again. No? We're good so far? All right. Then here is the finale part, when to eject. So basically we've talked about band-aids for the general linear model in terms of, well, you can switch the standard errors and you can add slopes and see if they matter and you can sort of work within the existing framework, but there are certain conditions in which that's just not going to be doable. So if constant variance is never going to be plausible, then that is where the world of generalized linear models comes in, where the "ized" part refers to the use of some kind of other distribution for the residuals besides normal. So these models differ in 2 respects. They pick up a different distribution, one that is a better fit to the data. So it turns out that there are distributions that match a lot of commonly used kinds of data. So if you have 2 outcomes, or excuse me, like 2 categories, binary, can you think of a distribution you may have seen that has that? Yeah, binomial or Bernoulli as a special case of that. For number correct, like proportion kinds of outcomes, you can hack a binomial for that. There's a family of count distributions for things that are bounded at 0. There are distributions for continuous outcomes that are skewed and bounded at 0. So gamma is one for that. And F is another one. No one uses it for that, but you could.
No, but...
Yeah. So there are other distributions out there, and it's a question of knowing which ones and how to access them in your code. The other piece is something you'll learn about called a link function that keeps the predictions within bounds. That's all I want to say about it right now. It's magic, though. It keeps you from predicting negative counts or probabilities of 1.2. So that's the follow-up class that I designed to go with this one deliberately, where these models are covered. So it's essentially all the stuff you did this semester again, but predicting different kinds of outcomes besides just continue-ish. As well, the last unit of it talks about multivariate models. So multivariate means multiple outcomes at the same time.
Cool.
So if you have mediation as a question, like X predicts M, and M in turn predicts Y, and I want to talk about how the relationship between X and Y differs after I control for M, mediation triangle, it's always depicted that way. That you can do that in a multivariate analysis called a path model or path analysis. So we're going to do those. They're super cool. And something that I did not learn about until I was already a tenured faculty member, and I wish I would have learned a long time before that, is quantile regression. So think back to week 1 of this class. What did we learn first? What was week 1? Besides me trying to walk you off the ledge and assure you that I'm not scary and that it's going to be okay. Descriptives.
Averages.
Yeah, like what's a mean, right? That's where we started. Look how far we've come. But there's other ways of characterizing central tendency, right? Can you think of another one? Or read from the screen? If you have a mean, you might also have
Median.
medians or modes. Well, no one cares about modes. That just goes out the window when it comes to predicting things. But
True.
predicting the median is something that you can do. So like the median home price, for instance, or
Weighted mean.
median income. What?
The weighted mean.
A weighted mean. Yeah.
So secondary data.
Yeah, so medians are better measures of central tendency in data that are skewed or that have outliers, where the outliers are kind of dragging the standard deviations away. And so you can predict the median in a regression model instead of the mean if you're worried about the effects of skewness and outliers. And if you can predict the median and you recognize that that's the 50th percentile, you can predict any percentile you want. So this is really useful in answering questions like, does my intervention work better in low ability children than in high ability children? Like, instead of predicting the 50th percentile of the mean, you could predict the 25th percentile and answer that question. How is the slope in this section of the variable versus that section of the variable? It's kind of like a piecewise model, but it's done in one continuous fashion. So I cover that as part of these because it's related to that.
Is that related to like the ITBS score? They do the 99th and the 70th and the 50th percentile, or no?
It could
be.
be. It could
Okay.
be. Like if you wanted to predict how do I predict who's going to be at the 75th
Yes.
percentile,
Yes.
right? Or else who's going to be at the 25th percentile? You can do that
Yes.
with these models.
Cool.
Yeah, they're super cool. They come in handy in a lot of cases. So I covered these things as part of that, but generalized is the main thing, is adding different kinds of outcomes. Another one, this is probably the biggest problem, is that general linear models are for independent samples.
Mm-hmm.
Meaning that the E from you and the E from me and the E from you are not any more related. Like there's no correlation in the residuals across people. No, there's no pockets of people who are more related to each other than others. That pretty much never happens. That's why I had a hard time finding example data for this class, is because like that is just not the world. So you will see this in scarier textbooks written as an assumption abbreviated IID. That stands for residuals are independently and identically distributed. That means independent, unrelated with constant variance. So when would you have this violated? Dependent sample t-test. That's something you probably would have learned in intro stat. Like if I have a pre-test and a post-test and I want to know if people changed over time. Sure. Can I use the models in this class on that kind of data? No, you cannot. Because the pre-test and post-test scores from the same person are probably more related than the ones from different people. So the way to fix it is essentially to estimate another kind of residual variance at the same time. So you have one that talks about differences between people, and then one that talks about differences across time. And they're two different things at the same time.
Vladimir. Sorry.
Yeah,
Yes.
and yes,
Yes.
my graduate student who's asking me questions about levels
Sorry,
of
I
analysis,
didn't-
that's exactly what he's talking about. Yep. So more generally, correlated residuals, or dependency, as it is sometimes called, result from sampling multiple dimensions simultaneously. So if you have multiple students you're interested in, but in order to get a large enough sample size, you need to go to multiple schools. Then we need like one kind of variance for student-to-student differences, and then another kind of variance for school-to-school differences. Longitudinal research, so this is my area of work, multiple occasions from the same person. The occasions from the same person are going to be more related than occasions from different people in almost every situation. So then I would need one kind of error term that's like, why do people differ from each other on average? and another that's like, why did you get a different score on this occasion than on the previous occasion? So there's like time variance and people variance. Now that sounds kind of cool, right? Like, sure. You're still grading me, so I'll nod. So ignoring this problem can lead you to completely incorrect results, both with respect to the fixed slopes, their standard errors, and the p-values. All of it can be wrong. The effective sample size that you end up with is going to be lower than your actual sample size. So another way of saying it is like if you have kids who are nested in schools, you don't have as many kids as you think you do. To the extent that the kids are correlated in their outcomes, it's kind of like they're redundant. So there are ways to compute what is known as an effective sample size, which is like how much actual unique pieces of information you have. And without taking that into account, the standard errors are going to be way off. The other issue is with respect to the slopes, is that each predictor then is really two different predictors. So if I have, let's go back to kids in classes or kids in schools again. If I measure something like how many hours the kids are read to at night, that could be related to their school performance, right? But if I think about families reading to their children as some sort of proxy for, like, I don't know, having the time, money, space, and ability to do that kind of thing with your child as opposed to working 4 jobs to keep ends meeting, then there may be commonality in how much the kids from the same school are read to. So schools may differ on average in the parenting behaviors of their students. So when you talk about the effect of being read to, it's like, no, is it literally the reading? Or is it all the other stuff that like makes this context different of being in a school where all the kids are read to? Like that can have a separate relationship. So that's the reason why you would want to choose a different path than a general linear model when you have either longitudinal data, or this kind, by the way, kids in schools is known as clustered data. Kids are clustered into naturally occurring groups. So research designs with variation across multiple dimensions of sampling simultaneously. We need a different kind of model that allows the residuals to be correlated when they need to. We need to be able to tell it, hey, can you let the pre-test and post-test from the same person be related? And hey, can you let all the kids that share the same classroom or school be related to each other, but not across classrooms or schools? You can do that. And you can have non-constant variance as a result in these models too. So for simple cases, like pre-test, post-test would be an example of a simpler one, that will be covered in the multivariate unit of the generalized class. You can just literally tell Stata or R, put a correlation between these two things. Thanks. It's that simple. For other situations, such as more than 2 occasions or different occasions across people, or children clustered into schools or things like that, you need a multi-level model. And that is essentially layers of general linear models happening at the same time. So you could put in characteristics of schools, and they could predict why some schools have better average outcomes. You could put in characteristics of kids and predict why some kids in the school have better outcomes than other kids in the school. So it's everything we did just at the same time with different levels of sampling. Fun, right? Yeah. So if you're like, what is this about? Here's a tutorial that I published a couple of years ago with a former student. I called it Catching Up on Multi-Level Modeling. And I wrote it from the perspective of like if you're trying to watch a new TV show and it's like in season 5 and you want to catch up with what you missed, like this is that. Like you're jumping into this world that's been around since the 1970s. This is a way to try and catch up on the research that's been happening more recently. These have synonyms. So what I call multi-level, you will also hear of as mixed effects models, where that part means in addition to fixed effects like we have, there's something called a random effect. A fixed effect is a constant, right? Like we have beta 1 that's the same for everybody. A random effect is a variable. Like each person could get their own version of beta 1. Yeah. And that's why I call fixed intercepts and slopes with the word fixed in front, because I know this is coming. In education, you will also hear these models called hierarchical linear models, or HLM. So these are all synonyms. These models are introduced in design of experiments, so that's a fall course that's offered every year. And then longitudinal and repeated measures are covered in this class, clustered is covered in that class. I do it as separate things. And likelihood estimation is the difference in how the machinery works for this. And that is a whole nother thing, which is why I did not cover dependent samples, t-tests, or random effects in this class, because to do it with least squares is what we've been doing is not ideal. So likelihood estimation is introduced in the first week of generalized, just in terms of the ideas here. So I put up, let me see here, 1 second. Yeah, I want to do that real quick. So on my website, on the course materials page here, I have the map that I sent out, I think a link to. So courses in ed measurement and statistics for us. So this will show you the ideal, I think, sequencing of these things and which classes can be taken concurrently and which ones are hierarchical. So anything that's on the same row, I think you can take at the same time and be okay. So like right here, you are here. You're an intermediate. The next thing that I would do would be one of these, probably these two in particular, because they are the gateway to a lot more things. And the measurement classes are kind of on this side of it, and these are also sequenced in ways that would make sense to take some things before others. So you can get down to like this row here, and then the last row are things that are offered a lot less frequently. But these are the choices that have been around right now. So I'm talking about this class, this one, and this one, as well as design of experiments within this here. Two more slides. A big assumption that we haven't talked about at all. These models are working with observed variables. That means that they are assuming the variables are perfectly measured, perfectly reliable, no measurement error whatsoever. Now, if you're going to measure something like temperature or rain output or something like that, that might be a reasonable thing. But if you're trying to measure self-esteem or even ability, like the tests that we give the kids have hundreds and hundreds of questions, and so they're more reliable perhaps as a result, but they're not going to be perfect. So everything that we're looking at relationships is going to be underrepresented to the extent that these things have measurement error. The more noise you have in your data, the harder it is to see the signal. So it is unlikely, at least in the social sciences, when we have these squishier constructs, that we don't have any measurement error. And it is the case that in your methods section, for instance, if you give a survey or a scale by which to measure this, you might be asked to compute and report reliability for that scale. And so a common measure of reliability is coefficient alpha. It's garbage, doesn't tell you anything, has lots of assumptions that are untested, and that's why. But then we don't do anything with that information. Like we'd say, okay, my scale has an alpha of 0.75, that's good enough. And then we pretend that it's perfectly measured in the analyses. Like there's a disconnect there. But there are ways that we can fix it. So measurement error will reduce the size of the variable relations captured and otherwise introduce bias. For instance, if you're thinking you're controlling for some covariate, you're not really if it's not being measured very well. You're not really fully controlling for what you think you are. To fix this, we would introduce something called a latent variable, which is unobserved. It's imaginary. It is built from what multiple outcomes have in common, under the idea that each outcome has error to it, but if we somehow borrow across them, we can get a better representation of the thing that we care about. So latent variables would be the way to solve this problem, such as if we have multiple item responses to measure a latent construct, and there are several different courses that you can take that involve latent variables. So item response theory is latent variables with binary and categorical outcomes. Factor analysis and structural equation models, that's a course that I teach, so I put a link here. That is coming back hopefully spring 26-ish. That one is latent variables with continuous or categorical outcomes. I cover IRT in that class as well, and then there's special topics that show up periodically that use latent variable models as well, such as Bayesian psychometric models that's happening right now. So those are the choices for those things. So now hopefully you can see why I saved all of this to the very end, because I didn't want to bum you out. Because you've learned a lot, right? You feel like you've learned a lot? The problem is that there's a lot more out there. And for most realistic research designs with real people, And all the complexity that that brings, these models may not be everything you need. So if you have non-constant variance, at a minimum, you might want to get heterogeneity corrected standard errors and see how much they differ, or use bootstrapping to get a standard error that may be a little more reliable. If your outcome residuals are not normal, you may need to switch to a generalized model that uses a different distribution than normal. If you have a dependent sample, then you need some kind of multivariate model that bakes in correlation of the outcomes from the same sampling unit. Kids from the same school, occasions from the same person, that kind of thing. If you don't have perfect measures, you may need to account for that using latent variables, or psychometric models is a synonym for that. The good news, you didn't waste your time, I promise. Everything that you learned will show up again in all of these models. It's just you're adding to them and making them more complex for the complexity that actually is in your data. So that's what I have. And I want to say in bold, thank you to all of you for sticking it out, showing up, getting your work done. I appreciate it. I know this stuff can be intimidating, and I hope that hopefully you feel a little more confident in what you're doing. I also hope to see you in classes again. And if I don't, that's okay too. I understand that everyone has their different priorities. I will also say one more thing, that because you've all been here all semester, you have earned the right to bother me in the future, okay? So when you sit down with your data in your life and you want to run a regression model and look at something, but you're not sure about this one thing and you want to send me an email, that's fine. It's totally fine, under one condition. That 5 years from now, when you're the expert and someone is coming to you for help with these models, you help them too. We continue to pay it forward, because I am forever indebted to the people that answer my questions still to this day. And hopefully you will have that same opportunity, and eventually I will be redundant and unnecessary and I can retire. That's my goal. Make myself obsolete. So thank you, all of you. Let us know if you need any help. Office hours all next week to finish things up, and otherwise have a great break. Can we clap it out? Yay, everyone. Yay, all of us. We made it. We did it. All right. Bye for now. Bye, Zoomers. Thank you for the comments.
I've only
Yay.
seen one live from you all semester.